Suddenly shifts into the X-ray and gamma range. Then I would not be able to see anything, either because I would very quickly be dead, or I would be blocking my own view in order to protect myself from the gamma radiation.
In his general theory of relativity, Albert Einstein said that gravitation bends space. Thus, even rays of light are diverted. Light is bent around a body. The body just has to be heavy enough.
So large masses, in particular, that means black holes can bend rays. That's hard to get our heads around. How can rays be bent? But it really is possible. And there are some truly bizarre examples of that, the most famous being the Hubble smiley. Let's take a look at it. What we see here is a Hubble photograph. You can make out the various dots, and each of these dots is an entire galaxy. So each dot contains around 100 billion stars. And here you can see a face, 2 eyes, 2 galaxies, a nose galaxy. But this ring, isn't a galaxy. We'll see in a second what it is. And out here, this circle is the outline of the face. The decisive point in this picture, however, is this little dot which you can see in the middle. It's a fairly large galaxy, but one that is a really long way off. It has a truly gigantic mass. Even further away behind the galaxy is a star. Light from it travels past this galaxy and is bent to such a degree that we see these circles here. This effect is known as gravitational lensing. To get a better understanding of this, we need to look at the entire picture from the side. Now the same situation, but zoomed in on this little galaxy which now appears as a large galaxy. You can see it here, and at the center is a black hole, indicated by this cross. So what happens? Well, in the background we have this star. We as observers are roughly here. So we are looking across the black hole and the galaxy towards the star. What can we see? Well, the star is emitting its light. But this light is not passing the galaxy in a straight line, but is bent towards our eye in every direction. In other words, if I take another direction around here, it again bends towards our eye. You now have to imagine that three-dimensionally. What do our eyes do? What are they seeing? We think that the ray of light is coming in a straight line from this point, or conversely, from this point. But since, in fact, all rays are traveling circularly around the galaxy, it looks as if there's a ring around this entire galaxy.
As described in the relativity theory, light moves on bent space-time. The phenomenon that becomes visible is known as an Einstein ring.
Could this effect also be used to see isolated black holes? After all, we know that there must be millions of them in our Milky Way. Basically, the answer is yes. Then there would be no bright point of light at this spot, just a bare black hole. And we would only see a ring like this. That would be a clear indication of an isolated black hole.
The closer we get to the black hole at the center of our galaxy, the greater the effect of its gravitation on us. We enter a world of bent space and curved time. While our spaceship is moving towards the event horizon, for us on board, time is passing quite normally. Gravitation is having the same effect on us as it has on our environment. But the time in which we are moving is expanding more and more. Seconds become years and then centuries. We don't see the black hole, but we feel it.
Since light is never emitted from a black hole, I would never see it. I would only ever feel the black hole through the gravitation which it exerts on me. In that respect, I wouldn't have anything particular to fear.
Insofern hätte ich jetzt hier nichts Besonderes zu befürchten. Ich würde natürlich
I would, of course, always expect to see a star here. After all, I am measuring gravitation. I am flying towards something which exerts a force of gravity, but is simply as black as the rest of space. If we could really see a black hole, we would presumably see a large black shadow. The best portrayal of that was in a film which appeared in cinemas some time ago. A large black hole was shown in the film Interstellar. In fact, the large black hole audiences saw was created by scientists. They determined what it would look like. It wasn't left to the imagination of some director. To design it, physicists applied the theory of relativity. You see a shadow, and around this shadow, there is a relatively bright ring of light. That, so to speak, is the light which is deflected around the shadow and then reaches you. The black hole bends the space around it, which acts like a lens. So what you get is this lens effect.
Black holes take our powers of imagination to their limits, but physics can explain every phenomenon up to the event horizon.
Every black hole exerts gravitational force. It's the same with our sun. If we flew to the sun and instead of moving around it on an orbit, simply switched off the engine and stationed ourselves in front of the sun would grab hold of us, and we would hurtle into it. The same with a black hole. If I place myself in front of a black hole, switch off the engine, my speed would be 0. Then it would pull me in, and at some time or other, I would be behind the event horizon and be gone. With the sun, there is no event horizon. There would just maybe be a small flame as I burned up. But in the end, there would be no difference.
Radiation exits a black hole at the speed of light and is invisible to the naked eye.
But if I had X-ray eyes or radio eyes, things would be totally different. Suddenly, everything would be totally bright. From close to a black hole, I would probably be able to observe radio jets and radio nodes being emitted.
In orbit around a black hole, we would encounter another phenomenon.
Let's assume I'm at the distance of a photon sphere from a black hole and fly around it. If I now emitted light forwards, it would travel around the black hole in a closed orbit. I would see the back of my own head the whole time. That would be really amusing.
That is only one of the bizarre effects that await us in the intangible depths of the universe.
In the meantime, we've entered orbit around this sphere. And what do we see? Well, when we look out, we see that the light is coming towards us. We would also see the masses falling into this black hole. Everything has become bluish. This is known as a Doppler displacement, or a blue shift, because the incident light gains energy, and this shifts it into the blue range. So things out there look rather unreal. We're starting to fly very quickly and are approaching the speed of light, but we are still in a stable orbit. In other words, we don't need to do anything. We're flying in a circle around this black hole. But now we have to watch out. When we approach to within 30 million kilometers, our orbit becomes unstable. A bit closer, and we would automatically fly into the black hole. We can only keep ourselves out by thrusting against the gravitational pull. 20 million kilometers out, and we would be powerless to stop ourselves flying into the black hole, never to be seen again. But that's not the case with light. Even at a distance of 20 million kilometers, light can still escape from the black holes. That's why we can still see something. But when the photons, the particles of light, have reached the event horizon, there's nothing they can do either. They orbit the black hole, and when they get closer, fall into it. And that's the reason why, with this event horizon, no photon can get out. We can no longer see anything, and that's why we have this black sphere in front of us.
For every black hole, there is a point from which there is no way back. It is the boundary at which nothingness begins.
The only distance from a black hole that can be defined is the event horizon, the curtain, so to speak. Up to that point, the world is in order. And beyond that, no one can say because a black hole conceals all information from me. Anyone who fell in could shout for all they were worth. If they were behind the event horizon, I wouldn't hear them.
Lost in space and time.
If you find yourself behind the event horizon, you are gone. Completely. You can't see from the outside, and you can't look out. No one can say what happens to the matter which is sucked in by black holes. As a physicist, you would say, it is gone. The information you had beforehand is also gone. This worries physicists, because that should not be the case. It contravenes certain fundamental laws of physics. Something must have happened to the matter, but our theories do not tell us what.
The event horizon, a border zone at which it would seem all life ends.
Life always means that there is structure which preserves itself. But perhaps in the final analysis, gravity is, after all, one huge grinder which destroys every structure. And gravity is more powerful in a black hole than all other forces. So I'd regard the chances of any form of life existing in a black hole as extremely slim.
One of the biggest hindrances to traveling through the universe are the astronomical distances involved. But Albert Einstein's theory of relativity could provide a solution. It offers an, albeit theoretical, shortcut.
If black holes bend space and time, couldn't that fact be used to create a wormhole? What is a wormhole exactly? Let's take a look. Let's imagine a three-dimensional space portrayed once again as a flat surface. We place a large mass in it. You can see that here, a black hole. For the time being, we can forget about the lower part. Then we again have this funnel. So here, space is bent as far as the black hole. And now Einstein says the following can happen. If this black hole is nearby and on the other side of a universe, which is also three-dimensional, we have here a flat surface. This black hole would also create a curvature, a funnel on the other side. So we would have a black hole and on the other side a white hole. But why black and white? Well, the black side would cause all matter, like a spaceship, to fall in here. A white hole would do exactly the opposite. It would spit this mass out again. In other words, the mass would fall in here and come out again on the other side. So it's clear that through a wormhole, a spaceship could end up in a totally different part of the universe. Einstein himself said that wormholes could exist. The question is, do they really? Unfortunately, we have not seen any sign of this anywhere in the universe. Another totally different question is, would it be at all possible to fly through these things? Could they be used as a shortcut to get from one part of space to another? The simple answer is no, they couldn't. That would never work. Why not? Well, imagine a spaceship flying into this black space. The hole would go zip because it's dynamically unstable. The lower part would separate from the upper part, leaving only the black hole. The spaceship would be trapped, and that would be that.
But a wormhole would be an easy way of saving a lot of distance and time.
A wormhole would be a shortcut through this curved space. Imagine if you have an apple and a worm crawling over the skin. As it moves from the top of the apple to the bottom along the outer surface, at some point or other the worm will arrive. Of course, it would get there much faster if it could go through the middle of the apple. This is the shortcut the worm would take. The surface of the apple, however, is two-dimensional, and the worm would have to munch its way through a third dimension. Take things a dimension higher, which is not something our brain is equipped for. Unfortunately, it's only designed for three-dimensional space. But this, roughly, is how we can envisage a wormhole. It's a shortcut in three-dimensional space. Theoretically, the general theory of relativity says this is possible. But wormholes would only be stable if there were a certain form of matter which we have not yet found evidence of. Only then would the openings of these wormholes, so to speak, really be stable. And no one has found proof of these anywhere in the universe. So experimental evidence that these wormholes exists is still lacking. If they did, that of course would be fantastic. The gigantic distances in the universe could be covered very quickly.
Consequently, Hollywood also makes use of wormholes to make travel through our universe possible. And in search of the meaning of the origin of life, physics doesn't come into it.
A journey into a wormhole could prove pretty dangerous. You would need a very stable spaceship because in this case, too, space-time would have to be bent open to an extreme degree. Bending space-time involves powerful gravitational forces over quite a short distance, and they could tear me apart. I need a very robust spaceship.
But wormholes are just a theory of astrophysics.
At present, nothing like that exists, but we can imagine it. Such ideas are acceptable. But at no point in the universe is there any indication that wormholes exist.
The James Webb Space Telescope will be a new celestial spy. It will hover above the Earth at a distance of 1.5 million kilometers. The telescope is the most expensive measuring instrument ever built. A cooperation of NASA, ESA, the European Space Agency, and the Canadian Aerospace Authority. Comprised of 18 segments, its main reflector has a diameter of 6.5 meters. A shield the size of a tennis court will protect the telescope from the sun's rays. On an orbit 1.5 million kilometers from the Earth, the telescope will take the deepest look so far into the endless reaches of the universe. Only in space will the telescope unfold to its full size. The James Webb Telescope is designed to peer into the very origins of our universe, studying the genesis of stars and galaxies and determining the role played in the universe by black holes. But it is with an observatory on Earth that scientists have opened a new window on space. Through it, they observed the collision of two black holes, the two monsters of gravitation, one with a mass of 29 suns, the other with one of 36 suns, cannoned into each other and fused to form a single black hole. The energy that was released shook space-time. For the first time, physicists were able to measure the vibrations from such a collision.
And what a collision it was. Two large black holes came close to each other, and in the end, they fused. These were two very heavy objects, which were also moving very fast. A lot of gravitational waves were generated, and these gravitational waves were registered on Earth.
Albert Einstein had predicted the existence of such gravitational waves, but it was only a century later that science was able to prove their existence. It was on September the 14th, 2015, that gravitational waves were detected by a special observatory in the United States.
Imagine, for example, that a gravitational wave was going to hit us. Space would start to oscillate. And with the help of lasers, I could then measure how the distance between two places has changed. But that's very difficult because this effect is incredibly minute. We're talking about first being able to measure a distance of 10 to the power of 22 meters over several kilometers.
The gravitational waves crossed a distance of 1.3 billion light-years before they reached us. Distortions in the structure of space and time. Gravitational wave astronomy promises a totally new view of the universe.
Gravitation waves are the heralds of gravity. It is rather like me throwing a stone into a pond. Then I see waves on the water, and that is how you can imagine gravitational waves.
Their discovery was a sensation.
The importance is totally fundamental. It is just as Einstein predicted. In the past, their existence could only be proved indirectly. Direct proof was lacking. So from a fundamental, not just an astronomical point of view, and also from the point of view of physics, it is highly important that this has been discovered.
These observations will also help us to better understand black holes.
Vermutlich sind es auch die schwarzen Löcher, die in den Zentren von den Galaxien sitzen.
The black holes located at the centers of galaxies regulate how much matter comes in and the degree to which stars in a galaxy can form.
Das heißt also, dieses schwarze Loch ist
This also means that a black hole is something of a feedback for stellar genesis in galaxies.
Sternentstehung in Galaxien.
In other words, black holes could regulate the formation of stars in the universe.
Sternentstehungsgeschichte im Universum.
Proof of gravity waves is another stepping stone along the path to knowledge. Up to now, only light and radio waves could be observed, and most of the cosmos doesn't emit any radiation at all. Yet gravity has an effect everywhere.
It shows that our theories are correct, that Einstein was actually right, that the laws of nature which we have must be valid.
Sagittarius A star. The supermassive black hole at the center of our Milky Way is about 26,000 light-years away. But scientists suspect that numerous smaller black holes are far closer to us. Meanwhile, our Earth quietly continues to trace its orbit in the solar system.
Here on Earth, we have no reason to be afraid. I think that what is alleged to take place in the LHC, that tiny black holes would be created, so it shouldn't be switched on, is absolute nonsense.
The LHC is the most powerful particle accelerator in the world. Here, protons are fired at one another at the speed of light. When the machine was started up for the first time in 2008, skeptics feared that the end of the world was nigh. Today, the accelerator runs at twice the original speed and still hasn't generated any black holes.
What takes place in the LHC happens every second in the atmosphere. And if black holes really were to form in the LHC, that would also happen all the time in the atmosphere. But we're still here, it seems.
If black holes could be created with the LHC, we wouldn't need to travel to the center of our galaxy.
Is it actually worth making a journey to the black hole at the center of our Milky Way? If you ask me, I would do it at once, and for two reasons. If we flew there, we would experience Einsteinian reality. We would see gravitational lensing. We would perhaps travel past a black hole or a wormhole, but we'd have to be careful not to fly into it. Otherwise, we would never get out alive. Imagine having a black hole in front of you, being the first human to see a real black hole. What a thrill that would be, but I wouldn't fly into it. Otherwise, I too would be a goner. I'd first fly around the black hole twice, maybe, and then return straight to Earth. And now comes the second important point. By the time I got back to Earth, 60,000 years would have passed on our planet. I would have made a genuine time journey into the future of humankind. What could be better than that?
Mysterious black holes. We are discovering more and more of them in our universe. Some of their fascinating secrets can even be deciphered. But as always, here too, science's explorers are only just setting out.